Welcome to this course on manufacturing for turbines. So in this lesson 19 of the course, we will see the deformation and machining processes which are used to manufacture steam turbines. So in the steam turbine assembly, it consists of several parts such as turbine housing, turbine blade, turbine shaft, turbine diaphragm, and several of the deformation and machining processes are used to manufacture these components of the steam turbine. Before we go into discussing the details on deformation and machining processes for steam turbine, we will take a quick recap on steam turbine. So steam turbine, they are used in both nuclear as well as fossil fuel based power plants to generate electricity. Here the steam first passes at high pressure in the high pressure turbine part, and then it enters the intermediate pressure, and then finally to 1 to 3 low pressure turbines. So these turbine parts form an essential assembly part of the steam turbines, which include housing, blade, shaft and diaphragm. So starting with this manufacturing process of deformation, because as we have seen in the previous lesson, the role of investment casting in giving the basic shape to the steam turbine blades. So after the investment casting, many a times there may be some inclusion, microporosity, or some sort of micro voids present in the structure of the turbine or the steam turbine which is cast. So in order to remove such defects, it is very essential to do the deformation, because in deformation based processes the refining of the microstructure takes place. So if we look at the casing and housing of the steam turbine, so deformation processes like rolling and bending are very useful. So in the rolling forms the initial shape or the basic shape of the casing from flat sheets, followed by bending to achieve the cylindrical form. So the benefits are to have they are very efficient to produce large consistent parts with smooth surfaces. And some of the important process parameters include consistent pressure application, controlled rolling speed, and bending angles. So if we tightly control the process parameters as mentioned, we can get the very good shape of this casing, which is very suitable for the steam turbine. Next process in the deformation based processes for the turbine include precision forging. So precision forging involves shaping the blade by applying compressive forces and by also allowing the blade material, that is the alloy, nickel chromium alloy, to flow within the die, because as the compressive force is applied, so there will be stresses generated. Compressive stresses, under the influence of compressive stresses, the material will flow in the die and it will take the shape of the die. So the benefits of precision forging, they include near net shape manufacturing. So whatever is the shape of the die, exactly the similar shape will be formed of the product once it takes the solidification, or it is basically deformed into the die. This also helps to enhance the grain structure. So what happens in all these deformation processes, by application of force, the forces lead to generation of stress. So now this stress which is generated is often beyond the yield point, and this stress often functions in the plastic deformation zone, and the stress value is always less than the ultimate tensile stress, so as to final fracture of the component does not take place. However, under this influence of the plastic deformation stresses, the material just flows, or just the shape of the material is changed. So while changing the shape, especially in forging or precision forging, the die, it has the limited volume in which the material has to flow, and upon compressing it and forcing it to flow within the same volume of material, so the microstructure generally refines because material will flow, and the micropores or porosity present or micro voids present will be filled up with the flow of the material. This basically leads to overall enhancement of the mechanical properties of the component, and the process parameters which are there, they include the right temperature. Often precision forging is conducted at high temperature, and proper pressure which will ensure the proper material flow within the die. So if we see the image showing the precision forging process, so here we can see that there is a table, and on the top part we have a ram which can move up and down to apply the compressive force. Then this ram is also having some springs attached, and in the spring we have the below the spring we have the dies in which the material is the blade is loaded, and then upon application of the compressive force, the dies are closed and the material is then allowed to flow within the die as shown here, and because of which it can take the shape of the die cavity. Another important point to note here is that during this material flow, almost negligible material is wasted in form of chips or any scrap. So the effectively the processes, they only change the shape of the material by applying stresses which are beyond the yield stress and within the plastic deformation zone of the material. So next, if we see how the microstructure refinement is done, especially on the shaft of the wind turbine. So here basically the processes of hot rolling and extrusion are utilized. So in the hot rolling, it shapes the metal into a long cylindrical form, and extrusion of this material, it ensures refinement of shape and dimensions. So the various benefits include production of shafts with excellent mechanical properties and surface finish, and parameters such as high temperature for rolling, precise die dimension, especially in case of extrusion, are very essential to get the right properties on the shaft. So here we can see a typical hot rolling process once the material passes through the two rolls. So these are the two rolls here, roll 1 and roll 2, through which the material is passing through, and we can see that as the rolls they compress the material, the grain structure gets refined as old grain structure breaks into formation of new and elongated grains, especially along the direction of rolling. Next is the manufacturing processes, deformation based processes which are used to manufacture the diaphragm of the steam turbine. So in the diaphragm manufacturing, the sheet metal forming processes are utilized. In sheet metal forming processes, processes like shearing, bending, stretch forming and deep drawing are utilized to change the shape of this sheet, and before doing that it also involves cutting of these high strength alloy steels sheets into required form of diaphragm. The sheet metal forming processes, they ensure dimensional accuracy, uniform thickness, which is very suitable for mass production. The various parameters in case of sheet metal forming involve controlled force application, to achieve the desired shape without compromising material integrity. So in this case, the diaphragm is essentially formed because of the sheets. For the shaft, we have the cylindrical based workpieces, and of course the blade, it is coming in from the casting process after investment casting, as discussed in the previous lesson. Next are basically the machining based processes which are used in manufacturing of the steam turbine. So in manufacturing of the steam turbine, the role of machining processes is to generate very smooth surface on the surface of the blades to ensure the proper aerodynamics shape is maintained for good efficiency of the steam turbine. So in this regard, the material which is used in steam turbine housing, this includes high strength alloys. So high strength alloys, typically they may be made up of some super alloys like inconel, or maybe some stainless steels or nickel chromium based high alloy steels, which ensure durability, resistance to high temperature and pressure. The technical overview here basically utilizes in machining. It is based on the conventional machining processes. So as we know, conventional machining processes are subtractive processes in which a tool which is generally harder than the workpiece, this removes material from the workpiece in form of chips. So in case of conventional machining, we have seen several processes in earlier classes such as turning, facing, drilling and milling. With respect to the steam turbines, it is the milling process which is very popular to develop the final shape with proper surface finish on the blade surface. So workpiece preparation is basically the first step for the milling, where material selection with respect to high alloy steel is chosen because of its durability, resistance to high temperature and pressure. The fixturing of these workpieces is another important aspect to consider, because in conventional machining it is the forces being applied when the tool interacts with the workpiece, because of which the shear stress is generated along the shear plane, which basically removes the material through the formation of chips. So in fixturing, the workpiece is securely clamped onto the milling machine, which using precision fixturing to ensure accuracy and repeatability. Next important criteria while machining steam turbines blades are basically the type of cutters or the cutting tool. So different types of modern milling cutters can be selected based on the geometry and features of the turbine housing. The cutters may also be chosen based on compatibility with the workpiece. Commonly, carbide, ceramic, or cubic boron nitride based cutters are utilized as the insert material. Now, in this case, the the cutting tool is basically the having several inserts or which can be indexed, and the utilization of inserts basically reduces the tool changing time and tool changing cost, because by indexing the inserts we can bring the new edge of the insert by to machine the workpiece quickly. And the materials of the insert, as mentioned, are very hard materials, and they are successful in machining the high alloy stainless steels which are containing significant proportion of nickel and chromium. So third important step is to set the milling parameters. So milling, as we know, is a conventional machining operation where a multi-point cutting tool interacts with the surface of the workpiece to remove material in form of chips. So cutting speed is the first important milling parameter, which is optimized for efficient material removal with minimal tool wear, because some amount of material is also removed from the tool, which is known as tool wear. And typically the material removal should take place at the rate of 100 to 300 meters per minute. Feed rate is another important criteria which balances the speed of machining with surface finish quality, which is typically of the order of 0.05 to 0.3 millimeter per tooth, because there may be several teeth on the milling tool. Depth of cut is the third important milling parameter, which maximizes the efficiency while avoiding tool overload. Typically, the depth of cut of the order of 0.5 millimeter to 3 millimeter is chosen depending on the operation. Next is the sequence of milling operations. So sequence of milling operations, they involve utilization of rough milling operation which removes bulk material quickly using larger cutters and aggressive feed rates. Then comes the semi-finish milling operation, in which it is utilized to refine the shape and dimensions with smaller cutters and precise feed rates. Third is the finish machining, which basically achieves the precise dimensions and surface finish using fine cutters and precise milling parameters. It is often seen the rough milling takes the minimum time, while the finish machining it takes the maximum time while the machining operation is progressing. Third important criteria here shown on the slide, and fifth in the sequence, is the coolant application. So coolants, as we know, are very essential in conventional machining because they help to take away the heat from the machining zone. They also prevent the formation of built-up edge on the cutting tool. So different types of coolants are used, especially in case of machining the steam turbine blades. High pressure coolant systems are used, which in this case several oil-based coolants may also be used to reduce friction and heat in the machining zone. Coolant delivery is directly done into the cutting zone through nozzles or internal channels of the cutter for effective cooling and lubrication. So if we see the overall processes which are utilized to manufacture the housing of the steam turbine, so this basically starts with the mold making, which is typically done using sand mold. Then we have the molding operation and sand cleaning is done. So after the cleaning is finished, so the casting of the housing is heat treated, riser are removed by grinding. So then some short blasting can be done to remove the any sand particles from the surface of the housing. Subsequently, the some types of destructive or non-destructive testing can be done to estimate the quality assurance of the housing which is cast, and sometimes some grinding or repair welding may be needed. Casting is finished and machined, and subsequently the finishing operations are put to use to create a good surface finishing on the housing. And once the appropriate surface finishing is achieved, the housing is then assembled with the steam turbine blade and other parts such as shaft and diaphragm. Next important uh, criteria or important component in the steam turbine comes to the blade. So there are several challenges in blade manufacturing or blade machining of steam turbines. So because at turbine blade operating at full load, it may reach very high speeds of the order of 500 meter per second. This results in a centripetal acceleration of the order of 160,000 meter per second square and centrifugal forces of the order of 550 tons. And moreover, the blades, they have a complex aerofoil shape in which the complex blade profile of difficult to cut materials such as inconel, they present significant challenges. So here the goal of any machining process is to produce faultless components that meet the stringent market requirements. As shown here is basically the low pressure last stage turbine blade which is failed because of some manufacturing defect. So even for machining the steam turbine blades, the conventional machining or conventional milling operation with very hard or modern cutting tools utilizing ceramic or CBN are used. The CNC or multi-axis CNC machines are utilized to machine the blade to ensure the accuracy and repeatability of the process, and excessive use of coolants is done so as the minimum heat generation takes place in the machining zone and blades are effectively machined. So here we can see a typical steam turbine blade being held in the headstock here, and the other is part is held in the tailstock, and a CNC milling cutter with the cutting tool here is then utilized to machine the surface of the steam turbine blade, and this steam turbine blade, the surface finishing is done by removing material in form of chips. So then what can be the machining solutions to machine the steam turbine blades? To overcome the challenges as mentioned previously, a precisely matched range of tools for both rough and finishing processes should be employed to handle the complex blade profiles and difficult to cut materials such as high strength alloy steels or inconel. Tool selection should be done to ensure advanced tools which are optimized for high strength alloys and complex geometries are used, which will ensure efficient material removal and precise finish. Roughening tools are also utilized to remove bulk material quickly while maintaining the stability and minimizing tool wear. So this process shapes the basic blade shape. Then are the finishing operations, which are basically utilization of finishing tools to provide high precision and surface quality of the turbine blades to ensure they meet the tight dimensional tolerance. Then another important component in steam turbine is the shaft, because the rotor and the blades are mounted on the shaft, and subsequently this shaft is also used to take the rotational power to the generator for generation of electricity. So turbine shafts are mainly machined through turning and groove cutting operations with some amounts of drilling. Large amounts of material are removed and demanding grooves to be cut. So materials for shaft, they include high strength steel and super alloys for durability and performance under extreme conditions. So machining operations involve turning, groove cutting and drilling to achieve the required shape and dimensions of the turbine shaft. So we can see here a typical cut section of the turbine shaft, where we can see various types of grooves being cut on this shaft and other stringent machining requirements, because the shaft has to further be assembled with other components of the steam turbine. So then we have the step-by-step machining operations, where we start with the rough turning with the objective to remove the bulk material to form the basic shape of the turbine shaft. The tooling utilized here is a heavy duty double-sided insert with the latest insert geometry. Parameters such as large depth of cut and high feed rates are utilized for efficient material removal. Challenges involve managing strong cutting forces and also ensuring the tool durability and edge security of the insert. Then is the groove cutting operation, which ensures precise grooves of specific features are manufactured on the turbine shaft. Here, the angled inserts are used to access difficult grooves with techniques to employ 90-degree angled insert for standard groove profiles. The benefits of using groove cutting is that we don't need any special tool. Standard blanks may be available for dedicated profiles. Then high pressure coolant application is also used to improve the chip control and tool life, especially in the finishing operations. And utilization of high pressure coolant systems enhance the cutting performance of the machining process. The advantages of utilizing high pressure coolant involve increased cutting speed and reduced thermal deformation. So a steam turbine is also consisting of moving and fixed blades, and stationary blades or the stator are often fixed on the diaphragm, which was previously given a basic shape using sheet metal forming processes. So this also helps to direct the steam flow onto the rotor blades and is made up of high strength alloy steels. And machining processes for diaphragm involve turning the outer and inner rings with precise dimensioning. High precision turning inserts are utilized, which may help to reduce the cycle time from 2 to 20 hours. Cutting parameters such as speed, depth of cut, and feed rates have to be optimized. Several grooves may also be needed here to hold the blades into their position, and again angled inserts are utilized here. Here also excessive use of high pressure coolant is done to increase the speed life and tool life and improve the chip control. So with this we have seen the processes which are used to basically manufacture the steam turbine in terms of deformation and machining processes. We will see the summary. So in summary we have mainly seen the deformation based processes which essentially utilized the processes such as rolling, which was specifically hot rolling, extrusion, then precision forging, and sheet metal operations. And in case of machining processes, we have seen processes like the conventional milling processes being used in the machining different parts of the steam turbine, which include housing, shaft, blades, as well as the stator blades, etc. So in the next lesson we will see laser metal direct fabrication processes used in the steam turbines. Thank you.